in the next 1 hour, I will try to present that LLM large language model in the application of some of the geotechnical engineering problem. So as we know that that AI has been used extensively in various geoengineering problems, but LLM is not so much used in the so far in the geoengineering problem. But what is the advantage we'll get it by if we use LLM than traditional AI approach? We'll see in this lecture. So what is the in the today presentations? I will talk about large language model. What is basic introduction, and then some of the sample application will show in the stability of the slope analysis. And next topic is the prediction of the seismic liquefaction of the soil. How we can apply large language model for prediction of the seismic liquefaction, and then some of the take-home message or conclusion from this presentation. So if you come back to the previously that AI application, I think everybody knows. I'm not going to the details. It is applied in various domain of the geotechnical engineer, site characterization, liquefactions, energy pile, tunnel, everywhere. It has been successfully used. But actually, if you look at that, what is AI? The issue is that when you are giving input, for example, if you want to calculate the bearing capacity of the soil, then when you are giving the input and data as a tabular form, for example, you will tell C is equal to 20 kPa, phi is equal to 35 degree, and gamma is equal to 18 km per meter cube, depth of foundation around 1.5 meter, and B is the width of the foundation as 1 meter. So you are giving as a data set, that means 20, 30, 5, 18, 1.5 and 1. But that when you are giving this as an input into the AI model, that model does not, that AI, basically AI does not know that what this parameter actually, that what this parameter, what is this 20, what is this 35, what is this 18, they have no idea. They have taken as a data actually, it's a number. But if you use LLM actually, they will give the input as they will define the input just like a human-like text. That means you will tell the AI that the value of the C is 20 kPa and angle of internal friction is 35 degree. Unit weight of the soil is 18 kilometer per meter cube. Depth of foundation is 1.5 meter, and width of the foundation is 1 meter. Then what will be the bearing capacity of the soil? So this type of input you will give to the model. So what will happen if you use this type of human-like text? Then automatically your training time you will get a huge amount of computational power to solve this problem. So you have to use the uh, deep neural network. That means basically it's use the transformer architecture, which is the deep neural network. Traditional neural network you cannot apply when you are developing the LLM model. That means in the LLM actually you will give the human-like text. So in the next slide I can explain what is happening. If you see that, for example, if you take a slope stability problem, so if you look at that in traditional AI, we generally give the 20.3, 10, 35, 40, 4.7, and 0.25. If you show this thing to anybody, any person who does not know about anything about the civil engineer, or even if he knows the civil engineering also or geotechnical engineering also, he has no idea that what is this 20.3, what is this 10, what is this 4.7, what is this 0.25. So traditional AI, if you give all these, they will also give the result. That is why this slope will be stable or it will be failure. But LLM actually will give that unit weight is equal to 20.3, cohesion is equal to 10, internal friction is equal to 35, slope angle is 40, and slope height is 4.7 meter, and pore water pressure ratio is 0.25, and then the model will give the stable failure. That means the computer will know all the data, what they are actually physically meaning. Previously, whatever we have used so far, the AI, more traditional AI, they cannot differentiate between the two data sets. For example, 20.3 and 35, what they are meaning, they don't know. They have taken as actually it's a number. So LLM will give you that so that people will understand also, and that AI model can understand that what type of input you are giving to the model. So as we know that development of the LLM model, you get the three stages. So first stage is the data preparation and sampling, that is just like traditional AI model, and then attention mechanism. This is very interesting thing, is the attention mechanism. So basically, if you look at that in traditional AI, generally we give the data set in tabular form. For example, if you give the Excel file, so but here actually you have to give everything is a human-like text. So that means when you are giving something, for example, you are telling pile. So pile, they will tell that attention, what type of next word, what would be the meaning. So whether pile foundation, whether pile settlement, or whether pile bearing capacity. So what type of words is matching with this pile, that is actually attention mechanism, and that we will use in the second step, and then third step is the LLM architecture. So next stage, we will try to pretend the model, pretending the model, and then we will in the pretending model, then we will make the foundation model, that is training loop, model evolution, and load pretend weights. That means whatever already in the model has been trained, you will again do the fine tuning to get the better result. And in the stage 3, you will get the data set with the class level. That means you will give the data set with the class level, whether the slope is stable slope or the fail slope. And then they will give the classifier whether the slope will be stable or it will be failed. So fine tuning is a one of the important step for developing the LLM model. Now coming back to the data set, actually, if you have collected the data set from the work of Lin et al. In 2022, it's a plenty of data set is there. There's a various information is there. The data set, there is gamma, C, phi, beta, and the H and porotar pressure coefficient. And actually, what is the status of the slope failure and stable failure? So this is actually tabular form. In traditional AI, this type of data you will take. But if you go by the LLM model, you have to give the that data set in the text sample you will give, and then we will use the text embedding model, and then this text embedding model will convert into the vector representation of the input. So in this way, whatever text you are giving, they will change into the vector. So how the learning has been done in the LLM model. So if you see that, so we are taking the data set, we are taking the internet textbooks or Wikipedia or the research articles. So whatever the raw data, unlabeled data is there. And then we will give to the pretend LLM model, and then we will give the text completion and the few short capabilities, and you train this model to give the classification and summarization and translation and personal assistant. So actually, in this case, in a slope stability case, for the slope stability problem, we will take it as a classification problem, because our input is the whether slope will be stable or it will be failed. But if you consider, for example, you want to calculate the factors of the slope, then you will go to the personal assistant problem. So that will be the regression type of problem. But it is my problem is that purely classification problem. So LLM architecture, if you see that the final GPT architecture, it's actually this is the final GPT architecture. So it is coming from the transformer block, and then we will go for the layer. First, we will get the layer normalization and JLU activations and fit for networks and the shortcut connection. So I will come all these parameters, all these things in the next slide. And I have used actually here training around 268 dataset has been used as a training dataset, and remaining testing dataset is used as a 78, and validation is the 39. So this validation has been checked whether there is a overfitting occur in the AI model or not. So if you come back to the now that LLM this thing, so for what you are doing actually here, you see that for one epoch is complete pass over the training data set. For each training batch you will give, and then the number of batches is determined by the training sets in the data. But how? By reset the loss or gradient from the previous epoch, calculate the loss in the on the current batch, backward pass to calculate the loss gradient, update the model weights using loss gradients, just like what we have done for the traditional neural network or deep neural network. All these things we will do in the here also. So similar type of approach will here also used. So how to transform a block is a very important in this in the for developing the LLM model. So if you look at that, that this is actually layer normalizations, and then the max multi-head attentions dropout will go, and that is called actually shortcut connection. And then you will go for the layer normalization, feed forward and dropout. So feed forward, if you see that, that is the linear and layer will use and JLU activation and with the linear layer. So this transformer block has been used to transform the your text data into the vector. So how do the layer normalization will use actually? So here actually layer input, if you look at that, where the 5 values represent a single training example. So we are using the 5 values. So here actually these 5 values are whatever the input values we are giving. So we want to make the zero mean and unit variance. So here the mean is coming, this is 0.22, 0.34, 0.00 and 0.22 and 0.00 and 0.00. So after layer normalization, it will change to the 0.61 and 1.41 and 0.87 and 0.58 minus 0.87 and minus 0.87. That means if you do all this mean actually that it will come to 0 and variance is the 1. So this is the layer normalization we are has been adopted for development of the LLM model. So if you look at that, how this happening actually. So if you see that there is an input we are giving here, and then you are tokenized text we are giving, and then token embedding layer and the positioning dropout, and then the layer normalization that's already I have told the shortcut, and then the transformer is coming. So if you see that in the GPT model, so there is a, if you see that there's a plenty of output is there. So if you see that there's a plenty of output, but in our case, the output is a binary. That means we'll get only two output here. One is the slope will be stable or it will be fell. So here actually, if you look at that, is a two output. One is the stable slope or the fell slope. So so that's why the here actually problem is a little bit easy than the previous problem, because their output is only two binary output, that is the whether slope will be stable or it will be fell. So training, if you look at, so training generally loss, if you look at, this is the loss actually. So as the epochs increase, the loss is decreasing. And if you see that around 45 epochs, that our training and validation loss almost same. So you have, I have kept that the loss should be within these 45 epochs. And then I have tried to check that performance of the training, testing, and validation data set. So if you see that when you are checking the performance of the LLM model, then one parameter is very important. That is the confusion matrix of the actual and predicted value. So confusion matrix for the training data set. See, this is actually predicted level. So when this is negative actually, and if it is this is the predicted level and this is the actual level. So if it is your result is positive but predicted level is negative, and that means we will take as a this will as a take as a false positive. And when your actual level is the negative, and your model is also predicting negative, then it's a true negative. Similarly, if your actual level but is negative, but your predicted level is positive, that is that is actually false negative. And so when actual data is your actual level is the positive and your predictability also positive, that is the true positive. So if you see that this is the actually confusion matrix of the for the training data set, and this is for the validation data set, and this is for the testing data set. So this is actually overall one graphical one representation of the prediction of the LLM model. But if you look at that, there is a no parameter is there in this case that how to check the accuracy of the model. So in this way, we have calculated that true positive, that is the accuracy, that is the true positive plus true negative, divided by the true positive plus true negative, plus false positive plus false negative, and precision is equal to true positive divided by the true positive plus false positive, and recall is the true positive plus true divided by the true positive plus false negative. F1 score is the 2 into precision into recall divided by the precision in recall. So if you look at in this case, so here actually performance is not so good because if you see that only 81% data is correctly classified for the slope stability data, whereas training data is around 95.45%. So, but actually, this model can be further tuned to get the better result if you add some other data or some other slope stability data also if it is available now. So that means you can get the better performance if you tune further. So next, my project is the prediction of the seismic liquefaction of the soil. As we know that seismic liquefaction potential of the soil, everybody knows. So I am not going to the details actually. So what I have done. So I have taken one large earthquake-based database of the SPD test. So SPD test actually here we have taken the depth of the soil, depth of the SPT value and fine content and N160. This is the water table depth, and Max peak ground acceleration and earthquake moment magnitude MW, and the total stress and the vertical stress and the liquefaction, whether liquefaction observed or not. That means when liquefaction observed, that is 1, and the non-liquefaction means 0. So this data has been used to develop the LLM model. So there are, if you look at, there are 1, 2, 3, 4, 5, 6, 7, 8. There's 8 input I have used. And for prediction of the liquefaction of the soil, that means here also there is a binary output, that is whether liquefaction will occur or not occur. So that is similar type of the slope stability problem. That means here also the problem is the classification. So how the LLM will develop in this case? So they will take as a human like text. So depth is 7.5 meter, fine content is 12.85, number of flows is 59.8, water table depth is 1.8 centimeter, peak ground is 0.4, earthquake magnitude is 7.4, total stress is 152.4 kPa, and effective vertical stress is 97.2 kPa. This is all input LLM will give, and their model will represent that whether it will be yes or no. So data set actually, if you look at, that is there are data set if you look at. So this is actually we have tried to develop some poverty distribution of the behavior data set and correlation between the data set. So this is the Z, that is the normal distribution, and this actually this this is Z, and this is actually your Z axis. This is FC. This is SPT value. This is total stress and vertical stress. So this actually your Z, and this is the normal distribution, and fine content and vertical stress. If you look at this is the fine content and vertical stress, and this is the total stress and fine content, and N160 versus fine content, and this is the FC actually your the normal distribution of the FC, distribution of the FC. So if you look at that, there is a relation between the total stress and Z. There is a quite a good correlation is there. So to develop to get an idea that how the data set is varying, that's why I have developed this plot. And the total data set has been used, that is the training data set and the validation data set and the testing data set. So here also training data set has been used as 70%, and the validation is 10%, and the testing data is 20%. So after doing this all things, then we have tried to train the LLM model. And if you look at that, this is the epochs that how the loss function is decreasing as the epochs is increasing. And here actually accuracy, how it is increasing. So we have taken that as the accuracy is coming around 70 epochs, that almost accuracy is almost same for the validation and the training accuracy. So I have taken around the 70 epochs. So this is the training and this is the accuracy versus epochs plot, and this is the loss versus epochs plot. So if you see that as the epochs is increasing, that around 70 epochs, that almost everything is coming same training accuracy and testing accuracy. So I have stopped the model at 70 epochs. So here also contribution matrix has been developed. If you see that, that is the that is one thing. It's very interesting that here actually on negative actual level is positive and the petty level is negative. That is almost that is quite coming zero. So add here actually the actual level, when actual level is positive and around the weighted level is positive, that is also 654 data is there. So this is for the training, and the second is the for the validation. Here actually if you look at that, when your actual level is positive and the weighted level is negative, that is actually it is 1. So only one data has been misclassified. That means it is a uh, false positive, that is only one data is there for the validation data set. And if you come in the testing data set, here also if you look at, that is your false positive, and that means the actual level is positive and the predicted level is negative, that is also only one. So I want to if you see that after doing all these things, then I have calculated that what is the how is the performance is coming. So if you see that here actually almost it's a quite good performance is there, and the testing is around 94.68%. That means almost out of 100 data, 94 data is correctly classified. So after that, I have done some tuning actually. So there is a plenty of parameters. If you look at, there is a plenty of parameters has some correlation. So for example, if you go back to the data test thing, you see that we have developed now finds content. I have taken an N160 and N160 and effective vertical stress. So there is a correlation between the total stress and the vertical stress also, and there is a correlation between the magnitude of earthquake and peak ground stress also. So I have taken only vertical stress and effective vertical stress and the peak ground acceleration and the N160 value. So other parameters I have not taken. So then I will check that how the model performance will check. So if you see that, so I have taken the peak ground acceleration 0.4 and effective vertical stress is 66.1 and SVD value is 11, because all of the parameter is quite related to the other parameter. Just like finds content will be there will be some relation with the SVD value. Similarly, effective stress will be some relation with the total stress, and peak ground acceleration also will be some relation with the magnitude of the earthquake, as well as depth also there will be some relation with the effective vertical stress. So I have not taken other parameter, and I will see that how this type of things what will be the performance of the now, whether the performance will be changed, and if it is changed, how much it will change. So the same things has been observed here. Actually, epochs, and this is the accuracy. And if you look at that, as here actually as the epochs is increasing, there is a difference between the training accuracy and the validation accuracy. So that's why I have stopped around here 25 epochs. So to get the better result, because 25 epochs, 25 epochs almost the accuracy is for both the cases almost same. So, and here also that 25 epochs, that means almost it is quite close to this actual training loss and the validation loss. So I have stopped the model around 25 epochs. And so here also confusion matrix has been developed, and if you look at, there is a huge change of the performance of the confusion matrix is there. Previously, if you look at, there's the true false positive. That means when actual result is positive and your predicted value is negative, that is coming almost 1, but here is 50. So there's a huge difference of the data set of the result. Similarly, for the validation also there is a difference is there. If you see that your false positive, that means actual result is positive but predicted is negative, that is false positive around 21. And testing also, if you look at that, actual is positive and the predicted result is negative, that means false positive is there. So now this is actually one of the visual representation of the confusion of the performance of the model. So now if you look at, so if you calculate that accuracy, actually, if you see that your testing accuracy has been reduced, almost 6% has been reduced, because we are using only less parameter. That means if you use the less parameter, that model is not giving good result. So it's better to use the many more parameters, just like we have done over the first model. So here actually testing has been coming around 88.56 percentage. So in this way, so that means so what I've tried to get a better result, but actual case it is not happening. So that means you have to use the many parameters to determine the liquefaction potential of the soil. So what is the conclusion actually? What is the take-home message we can give in an industry for context? As we know that the collection of the comprehensive evaluation of the data from many different sources, as well as customers, will become the standard to support real-time decision making. That means in industry for context, data will be one of the key role for any civil engineering project. So the rapid advancement of the LLM as well as AI present a huge opportunity to the geotechnical engineering for using the data effectively. So if you look at that, every day, everywhere, we are getting some data set every day, because geotechnical testing is going all over the world, everywhere. So every day we are getting the new data set. That means there's a plenty of option, plenty of opportunities there to use this data set for to do the geotechnical correlation as well as geotechnical for solving the geotechnical problem. So LLM can be used effectively. But second thing is some limitation is also there to this use this AI model. So some of the ethical concerns and digital division security compliance issues must be addressed to ensure the responsible and equitable deployment of the LLM solution. That means whatever solution you are getting by using LLM, that you cannot use, you cannot believe 100%. So ultimately, we as a geoengineer, we have to take the decision that what type of site condition and what type of everything is there, geology condition, everything we have to take into consideration before taking any decision. So thanks. Actually, this work has been done with me one of my MTech student, Rudranan. He's doing the currently MTech with me. And thanks to the Professor Reddy to giving me this opportunity to present this webinar. And this is some of the published book of my that is available. This is actually in Elsevier. Elsevier, they have invited me to write a book on this handbook of neural computation. This is in Springer. This is CRC Press, and this is also in Elsevier. So this all books are available into the Elsevier and CRC Press website. And thanks for your kind attention, and questions are welcome. And if you have any question, you can mail me also. Otherwise, you can ask me now.